right, cool. Hopefully we're wrapped up with project number 3. Module 3 is done. So we're 75% of the way there. Only one more module to go. And then we'll have some time to like go back and either work on previous work, like revise previous work, or try module 5 if you want to do like something new, and it's all just extra credit work for module 5. And here, I'll pull up our Husky CT. Yep, so there's an announcement about mid-semester participation. So that was one of the things that I wanted to pull up, was this link to zoom in some, like overall, like where are you gauging your participation right now. We'll throw out whatever grade you put here, we're going to throw it out and put a final grade at the end of the semester, the final participation assessment. But I do want to know like how you feel like you're part of the class right now. So if you're joining online, then what are some things that you're doing online that are like helping you be part of a learning community this semester? In class, we've been talking about numerical methods and Python and debugging and all sorts of stuff. So yeah, like how are you contacting people, how you're absorbing content and then also thinking about like your career and how this class sort of fits into that story of your career growth. Have you been working on any of these, like 8? These are 8 skills that across every industry, whether it's engineering or business or anything else. These are skills that if you have like stories and projects to demonstrate these kind of skills, and you usually advance in your career. So how does this class connect to those kind of skills? And then yeah, share some examples and all that. And we'll do the same thing at the end of the semester, but I just want to get a sense of what's going on for now. Ideally, I would have sent this out like 2 weeks ago, but time flies, man. There's just like so much going on, and like senior design presentations, it's just a lot of communications and stuff going on. Cool. And then we'll take a look at our kind of calendar. That can't be right. October. Oh yeah, that's October. Oh my god. Like homework. Next homework's due in 2 days. No, we have 2 weeks. That was the plan. 2 weeks. So get everything done before Thanksgiving break, so that when we get back from Thanksgiving break, there's nothing required that's new. If you want to do new stuff, great. Challenge yourself, push yourself into something new. If not, I get it. It's yeah. It is not required. No. Yep. It's just so whatever like homework 3 is worth. I forget exactly how it breaks down. Let's get up to our syllabus and grading scale. No, grading. Yeah, so like project 1, 2, 3, and 4 are all worth 10%. If you do project 5, you can get 110%. If you do homework 5, now you can get 1/4 of 30%, 30 over 4 point, anyway, 30 over 4. I should know this. 3/4, so 7.5. So 77.5% extra. There we go. Cool. Are you, yeah, where do we want to go for today? Jump into module 4 tour, or back up, like review anything? 4 tour, tour of 4, like a tour or specific? Okay, let's do a big overview. Where are we going here? Yep. Yeah, we're jumping into the matrix. So module 4 is specifically linear algebra for like engineering problems. So this would include like all the thermodynamic steady state, or thermodynamic and heat transfer steady state kind of stuff. All of that is linear algebra problems, because usually you have so many unknowns and so many equations, and that's how you can solve it. You can also start to solve like systems of differential equations with linear algebra as well. So if you can set up like, okay, here's variable 1, this differential equation, then we can start to lump them all into like matrix vector output. So if you have, so I'm saying that because if you haven't taken linear algebra, you're not behind. Like we're getting, this is just introducing like how to set up equation, like systems of equations, and then specifically how to solve them, like what to do with those systems. Linear algebra gets a lot deeper into the theory of when you have a system of equations, what are all the different like math operations and what are the properties of those systems. We're not going to deal with any of that. Like a little bit of like transposing and we're not really inverting matrices, but that's about it. Like we're not dealing with the theory of linear algebra, very much applied. Yeah, and because it's numerical methods, like we have to deal with the fact that you can't solve every system of equations equally. So the condition of the matrix is a measure of how solvable all are these problems. And we'll take a look at that. That's what this first module kind of builds up to, or first reading. And then Gauss elimination. If you have done linear algebra, this is like the standard way of solving a set of equations, or like kind of deleting or turning each row into a whole bunch of zeros and then kind of back solve your way through it. We'll apply like how to do that with computers and kind of see like what those functions look like. And then revisiting linear regression. So far we've done like straight line fits and like quadratic fits, but a linear regression can be anything. It can be any function as long as the constants that you're solving for, you can pull those out of the equation. So if it's like sines and cosines or exponential curves, like all that stuff, you can get the constant out and then create this like matrix Z, which is all the different operations that you're doing on your independent variable. And we can do least squares that way too. So kind of tying it back into like module 2. Well, a little bit, yeah, I guess it was mostly module 2 where we were doing like data analysis kind of stuff. Yeah. And then the project, all that's kind of building. So again, like anything that is steady state or static kind of solutions, if you turn it into a computer problem, it is a linear algebra problem. So finite elements is a linear algebra problem. It is like a boundary value problem, but when you start splitting it up, that boundary value problem just turns into k times x equals f. So we're not going to do the mesh generation, which is its own kind of field of, I don't know, where would you do mesh generation studies? It's not really mechanical engineering. We use meshes all the time for finite elements, but we're not like developing new ones. I feel like it's a computer science kind of problem. A little bit of engineering. So we're not going to generate the mesh, but we're going to focus on the actual like solution step of, okay, we have this big stiffness matrix. I want to solve it. What can I do with that solution? So some solving, the solving part, and then the post-processing. Like, what do the results mean? So that's module 4 in a nutshell. Actually, yeah, let's jump in here. Go right into 01. So I'm just looking at like this first example in that first reading. Like if we have 3 variables and 3 equations, one way to solve it is like I could say, all right, x1 is going to be equal to 1 minus 3x2 divided by 5. So now I have a solution for x1. Plug that into the other 2 equations, and then solve for x2, and then go through that way. But if I have it all set up, if I can get it into this form of like, here's my matrix, this is all my unknown stuff, all the x1, 2, and 3, it's all equal to some output, some known output, then for a computer, this is a very easy problem. I can just say, hey computer, I have a matrix that looks like this, and I have, that one looks different than what we started with though.
Yeah, I think that's for the like next exercise.
Oh, is it? I'm gonna change it back anyway. 5, 3, 0, 1, 2, 3. And then 1, 1, 1. I can define A, define B, and then tell NumPy solve it. And then the solution, at least the solution that this one comes up with, is like that 5, 3, and 0 times 20 will give me 1. Is that right? 5 times 20 plus 3 times 20. That can't be right, right?
It should be
5 times 20, 3
3 times 32 though. Is it doing the
Oh yeah, minus, yeah. Yep, yeah, so we're doing this row times this column to get that one. Yeah, so 5 times 20, 100 minus 3 times 33. Now we get to 1. There we go. Yep. So 100 minus 99 is 1. All right, we're good. I just gotta follow my own math. Yeah, and stuff like this where you have, if you're trying to look at what is a steady state mixing, like we have concentration in tank 1, concentration tank 2, tank 3. I know the flow rates that's mixing between them. I can set up like a conservation of mass, and all that is going to give me like for 3 concentrations, I've got 3 mass flow conservation problems, and I can solve what are like how much mass per liter was in each tank. Yeah. And then I'm gonna jump down to some nice dynamics problems. So with this set of equations, if x plus y is 3 and 2x plus 2y equals 6, I have 2 equations, 2 unknowns. But if I ask for a solution, I get this singular matrix error. Do you know why that happens? Yeah, it's the same equation just multiplied by, like, equation 2 is 2 times equation 1. Why can't you solve, why isn't that solvable? Infinite solutions, right? Because one way you can think about, is this in the next? Yeah, we'll just do it right here. Morning. Oh, I wanted to do it above there. No, I want to do it here. Let's go -5 to 5. So if I've got like x plus y equals 3, 2x plus 2y equals 6, these are linear equations. Like I could solve for y and say that y is 3 minus x. And then I could say that 2y is going to be 6 minus x over 2. So I could plot x and 3 minus x. And let's do like squares there. Because when we're trying to solve like a set of equations, we're looking for when does one line intersect another line, and it might be like 2 planes. Where the 2 planes intersect, it'll describe a line, and if it's 3 planes, then that line intersects that plane at one point, and then 5, 6. You can hyperdimensional kind of thing. Oh, plot is not defined. Now let's just define it here. That's not right. Oh, times 2x. That would be solvable. But if you have two equations that are just scalar versions of each other, then they're still describing like the same line. So the number of solutions that we get is infinite, just like you were saying. The lines are right on top of each other. So whether I want to say the answer is 2 or the answer is -4, like it is an acceptable answer. So it's not that there's no answer when there's a singular matrix. It's just that we have an infinite number of answers. It can be it can't be anything, but it can be an infinite number of things. Because I can't say that x is 3 and y is 2, but I could say x is 3, y is 0, something like that. Yeah. And then singular matrices, that happens when we get like super close. So like if this wasn't 3, but it was actually 3.0001, technically there is one intersection. It's really hard to see where that is because because the lines are so close to each other. And let's try it. Oh, I guess that one can't be the same. That one doesn't matter. Sorry. So we're going to say 1 and 1, and then we'll say 2 and 2. Three and 6. So this one doesn't matter. But if this was like 2.0001, like that, then equation 2 would have three and 0. So these two lines, they are intersecting at one point, but because it's so close to being a singular matrix, if you visually look at it, it looks like the two lines are the same. So when you have a singular matrix, or what's called ill-conditioned, it means that you're defining equations that are almost but not quite the same equation. That happens a lot. In finite elements, a lot of times it'll tell you, like, you have an ill-conditioned matrix, and usually, well, FEA and CFD both have the same errors that pop up. And usually it's your boundary conditions, something about it. Or sometimes it's like you're trying to solve a problem of, like, I want to know when this steel rod, like this big thick steel rod, is pressing on a super compliant rubber thing. The steel is basically not gonna have any strain at all as it presses on the rubber, and meanwhile rubber is gonna deform like crazy in the solution. So then you end up with a really stiff problem, and that can also lead to these same kind of issues, like where the the solutions that you're looking for are on lines that are almost directly on top of each other. All right, that was the long tour. Cool. Yeah.
So in this first module, can you explain the doc format of your exercise 1.1, or the very top, just the formatting of the print statement?
Yeah. In this one?
Yes.
So you can use that star to grab all the values in an array.
Okay.
So when I ask for A is 0, it has 3 values in that first row.
And so populate those first 3 curly brackets.
Yeah, as long as I have 3 curly brackets for it to fill up.
And if you just had 2, it would spit out an error.
Yeah, like I think if I remove this one, yeah, it just says like, hey, what do you want me to do with all this stuff?
And what does the 5 represent after the colon?
That one gives a uniform spacing, so it gives 5, that the whole thing is going to be at least 5 spaces.
So that way you create just a nice looking matrix.
Yeah, yep. Yeah, like if I change one of these to 1, well, then it doesn't look so bad. I guess because I changed the first one. So if I change, let's change like, these are all kind of uniform, right? Yeah, if I change it to 3, then it kind of butts up the next one.
0.1 is like the sig things, right?
Yeah, and that's how many,
Yeah.
the 0.1 after is how many decimal places I want to use. Yeah, getting deep into formatting and regex kind of stuff. Yeah, and I guess I could have put the star in here since I'm just plugging in a string anyway, but the star and the equals, but those are just getting dropped. Anytime you have a curly brackets like that, it's going to drop in whatever it is, and if it knows what object it is, then it's just going to try to format it as best it can. The usually floating point numbers, you have to kind of massage how many decimal points and how big they are, because they can get a little messy as it tries to print them with the print statement.
When you do format like that, does it round it all, or does it just give that decimal point at that time?
That one, it does round. Yeah, because it doesn't truncate. Is that, yeah. So just changing whether I wanted 1 or 5. So now the whole thing is like 5 long, and then those weren't great examples.
Very unfortunate.
Yeah, 4. Let's try 4, right? Yeah, so it does take that 159 round up to 1416. So those did truncate, but not specifically because it's truncating. Yeah. And I know there are, like, you can change the option, like the default print options. So right now it's showing how many decimals? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I think by default it shows 15 values. Mostly because, like, if you get 10 to the negative 16, everything below that is basically 0. Like, you can't do much with it. But you can ask for as many as you want. They're not gonna be accurate, but they're there. Like, it is stored as that number. You can even, I think at some point you start getting zeros, right? Yeah. Because at some point, even the computer is like, I don't know. Like, I guess zeros after that. If you ask for 100 digits of pi, the computer doesn't have 100 digits of pi. Really, I think we run out, I forget, like somewhere around here, mismatches. One four one five nine two six five three five 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 8 9 7 9 9 3, and then all the after that 9 3, we get 11599, but the actual value is 23846. It's approximate. Yeah. Yeah. Because here, like, every number that you store in a computer is approximated. Even numbers that seem like they're exact, because it has to be stored as bits, which are 2 to the something power, and we only have, I think, 50, like 2 to the something powers. Yeah, 52 bits for the fraction, 11 bits for the exponent, and then we use up 1 bit just to say, is it positive or negative? So once I use up all those bits to say, like, okay, this is as good as I can store pi, I have to round to one or the other. It's just, kind of think about it like you have a ruler, and you only have so many marks on your ruler. At some point you have to say, like, it's either one mark or the other. At least that's how we have to do it with a computer, because we can't, there's no way to say, like, well, it's just like a part of a bit of the way there. It's just like another fifth of a bit. It's like, no, it's either 0 or 1. Yeah, yeah, we can just use salt. We can say enough salt. Oh wait, are you solving this problem? Okay, yeah. Yeah. At least if you want to see all four. That one worked. You don't know. You're trying to solve all five. You're addition five. Look, one way to think about it is here and here is squish. But then here and here, squish it this way. Still the same. I can still solve the same problem, but all the versus squish it this way. Now or I can squish it and move it. Whenever you're in this happens all the time, find it. The boundary conditions, they all make sense. All of those things are allowed. And in resolution, how does it know it's in resolution? So there's two ways to solve it. One, you can like pick a boundary and say infinite. Another one, split it down the middle and say this as we were kind of looking at module 1 in that first reading, one of the things I was talking about was like equations that are linearly dependent. So in that first case that we were thinking about, it's just equation 2 was 2 times equation 1. Sometimes it's not as clear that there is linear dependence between the equations. Like in this case, we're trying to model like springs and masses being compressed. So I have force on one side and force on the other side, and overall we're trying to take this and squish it together, like and we're just looking at it because it comes up with an error when you try to solve this. It says you have a singular matrix, but it's not. At first it doesn't seem clear because it's like, well, I have a force here, I have a force there, some of the forces is 0, all the springs should be like compressing, but physically what that means whenever you get that singular matrix is like I could squish it and slide it, and it's still I'm still solving the problem that some of the forces is 0, because that's the only thing that I'm trying to solve. Or I could hold x5 at 0 and squish it, and now I still have the solution. Or same thing, I could hold x1 and squish them all. Or x3 could be 0, and now like x1 and x5 are both negatives of each other. They're both sliding the same amount but in opposite directions. So we end up with that same case where it's singular not because there's no solution, but because there's infinite number of solutions. We can't say that it's anything, but we can solve for lots of different values. And the way to solve that, and same thing with when FEA tells you that you have a singular matrix, usually you just need an extra boundary condition, like, okay, just don't let this point in my model move. Just fix it. Don't let it go anywhere. And then it's like, oh yeah, that's fine. You're good. Because that problem's a lot easier to solve, even though it's the same problem. Yeah, and sure enough, if we try that in here, I get this. So K, I did some fancy diag commands to get that diagonal, the tridiagonal matrix, where those two things that are not quite the diagonal but one off of it, you can add those in there. But when I try to solve it, it tells me like, hey man, you don't know what you're talking about. It's singular. And again, singular usually means infinite solutions, not no solutions. So usually there's a way to fix it. It means you're on the right track. You're probably setting things up right, but you need like one more boundary condition. And the condition number, the bigger that number is, the less likely you're actually going to solve the problem, because it's either singular, like it is a singular matrix, there's some kind of linear dependence between your problems, or it's really close to singular. So it's going to introduce a lot of error. And if it's 10 to the 16, then that's bad, because we can only solve things to like 10 to the negative 16 worth of work. Oh, this one.
The one before. Where we saw, yeah.
Just print K or sorry. Oh,
No, no.
yeah. Sorry, the next line down. I just realized.
There's a delay.
Yeah, there's a delay.
I'm not gonna ask that.
Yeah. Okay. So this condition linal dot condition of K. Oh, there's no linalf. Linalg. So like matrices don't have like a specific magnitude. Like if we have a vector, usually we can think of like, all right, if this is my vector, it has a certain magnitude and a certain direction. But a matrix really doesn't have the same thing. Like I can't just say that it's like a magnitude in 3 directions or something. Sometime you can kind of think of it, it's like maybe it has 3 directions and 3 magnitudes, something like that. But the norm is a measure of like, if I have this big matrix, what is the norm of it? So like one example is like we'll take like the max of the absolute values of everything and sum those up like along each row or along each column, and that's one way of finding the norm. And the condition is going to be the ratio of the norm of the matrix to its inverse. So invert the matrix, get the norm. And if that is really big, then it means that it's very hard to invert that matrix. But at least for us, it's the condition is just a number of like how easy is it to solve this set of equations. So the bigger it is, the harder it is to solve. Okay, yeah. And then in the second reading, kind of gets a little more into, or actually, I guess that's the first one. It gets a little more into like, what is the condition? Oh yeah, but we're out of time. Time flies. Thanks a lot.